All right, everyone. Thanks for having me back this year. My name is Patrick. I'm a senior PhD student with Dr. Travis Esau. And I do a lot of work with machine vision and artificial intelligence and trying to utilize those tools to improve sustainability for our industry. With that, there are two main goals to my research. The first is to develop a smart sprayer that uses machine vision to look for areas of the field that need inputs like herbicides. For instance, if you have a patch of weeds in an area, spray your product only on that area and leave the blueberry plants alone without those inputs, so we can save money and save herbicide inputs using that method. And the second part of my project is developing some tools for field scouting, such as bud stage detection, like our F2 growing degree day model, what he was doing, weed identification and disease identification. So I mentioned AI. To open up, I do want to talk about maybe what that is, so we all have the same definition. And because it is a buzzword, we hear a lot in the traditional media and social media these days. But overall, it's just a computer system that can perform tasks that are usually require human intelligence. And with that, we can do some really powerful things. And if you need evidence of that, you just have to look at this definition. I didn't write that. I had an AI chatbot write that for me. With that, when we're talking about AI, we are usually talking about a subset called machine learning, where we give the computers data to learn from, ask them to solve the problem, and they sort through that data and find the solution. With that, a more specific technique is called deep learning, which is where we model our AI after what's going on in a mammalian brain. So on the left-hand side of the screen here, we have what's an artificial mathematical model of a neuron. That was developed actually in the 1950s. And quickly, computer programmers realized that they could chain these together into these artificial brains, like what you see on the right. You see a very simple one. And we typically organize these neurons into groups or layers. So we have those three inputs that are sort of that light green color. We have two layers of these blue neurons that will do our calculations for us, and then two output neurons. So for instance, it could be, a weed or not a weed if we had two output neurons, yes or no. Or if you're not doing stuff in our industry, maybe is this a cat or a dog? Is this, a chair or a table? If we have two, and if we want to have more options, we need to add more neurons at the end. Now, for image analysis, we usually don't have them lined up in straight lines like what we see there. We will usually put them in some sort of a rectangular prism like what you see in the bottom graph. That's how we're going to lay those out. And with that, you can pass images into this, and with lots of training data and training examples labeled. So for instance, if you show the computer pictures of horses, tell it it's a horse. Show pictures of cars and dogs, say it's a car or a dog. With enough examples, these algorithms will learn what they are. And what we have done so far is harness that for detecting weeds in wild blueberry fields. So in this video, you'll see some examples of hair fescue and sheep sorrel in May. Most of these pictures were captured in 2019, 2020. And we used those images for hair fescue. We took around 4,200, had to label all of those with bounding boxes to point out where they were. And we developed a model that could actually just pick it out in real time with a very high level of accuracy. Same thing with sheep sorrel. We used about 2,500, I think, for sheep sorrel, but it's the same idea. So that's the background on the project. That was a few years ago we did that, and since then we've been trying to harness this and put it into something that is usable on a sprayer. So to make a machine vision smart sprayer, we need some components to actually operate with those neural networks. First, we're going to need cameras that can operate in real time and take those pictures. Then we need some sort of a computer to run those cameras and process the images through that convolutional neural network, or CNN. We'll need some nozzles that we can turn off and on as quickly as we need to. We need some sort of a controller for these nozzles so they can take the outputs from that neural network to decide what the nozzle should be doing. And finally, we need some communication lines. And then all of those moving parts need to operate in real time and communicate nicely with one another. So to start out, in my talk here last year, I talked about the whole process of how you select a camera. We looked at different cameras at different price points. The FLIR Blackfly S with that lens is about $1,000 versus that Logitech C920 is about 90 these days. What we decided on though was a very similar one to what you see in the top left, the Oak D. Now that is a 3D camera. I'm not using the 3D functionality on it, but the other key feature is that it actually has a processor on board that's designed for processing these convolutional neural networks. So we don't need a computer outside to actually process those images. The camera does it for us. It saves us some work. We went with a slightly different variation. What we noticed on our sprayer was when you have a camera like a webcam or in your phone, you might notice that you can adjust the focus on it. So if you're looking at something, really close, the lens will automatically move to make sure it's sharp. The vibrations on a sprayer will knock that lens out of focus, so you will not get sharp images consistently. This camera, the lens is fixed. You can't adjust it at all, and that prevents those errors due to vibration. So that's the camera figured out. And in part, the processor. These cameras, though, need a computer to basically tell it when to take a picture. So we need some sort of a computer system. These cameras operate on USB cables. So what we decided to use were these small single board computers. At the time we purchased these, we figured that we might be doing the processing on the computer, not the camera. That's why these specific ones from NVIDIA were spec'd out, because they can do that AI processing. In truth, you could use any real single board computer with 3 USB ports on it, or even potentially a phone with a USB hub in it. You just need something that you can plug these cameras into and press record. So that's our processor. Now we need some actuating nozzles. So solenoid valves have been sort of a gold standard for a while in our research space. And we've managed to acquire some ones that worked on the ISOBUS system for this project. ISOBUS was developed in the 1990s to really help with interoperability between tractor components. So if you had an implement from one manufacturer and a tractor from another, those two devices would play nice with one another. You could get your tractor from John Deere, you could get something else from Case, and they would just work together. So Pentair was able to provide us with these nozzles that they make that operate on this ISOBUS system. The other advantage to ISOBUS is its reliability. Instead of just using a single wire for sending our data over, we use 2 wires that are twisted together. And in the graph that you see at the bottom there, that's the differential signal between those 2 wires. Whether those voltages are the same or different is what's looked at. So if you have interference, let's say, there's a spike in your battery, those 2 signals will be affected equally. So it's really robust to noise and really reliable. With this Pentair system, on the virtual terminal in your tractor, you can actuate these nozzles basically by hand. You have one button in green there for every nozzle on your sprayer. And then this is designed so you have full control over what's being sprayed and when. Now our system taps into this and takes over from that. We turn all the nozzles off and then we turn them on with using the cameras. So now we need some sort of a device that is going to actually talk to the nozzles from my system. So we worked with another lab on campus on this, who are working actually in the potato industry with McCain in New Brunswick. There's an electrical engineer on their team who's really familiar with ISOBUS. So he helped us develop this box here that basically, if we look at the top button here, machine vision system, that's mine. I just plug right into this, and then he plugs into the ISOBUS system. And as of this past spring, everything seems to be playing really nicely together. So finally, we need to tie this all together. So we have 2 sprayers that we use in our lab. I'll show you some pictures in a minute, but this is an example of how we wired it up on our 12 nozzle sprayer. We have 1 camera for every 2 nozzles. So if there's a weed in the left-hand side of the image, it will turn on the left nozzle. If this camera sees one on the right-hand side of the image, it turns on the right nozzle. We plugged 3 cameras into one of these single board computers. And then what we did to expand this out is use multiple of these small, inexpensive computers and run them on an internet network. A question I got about this a few weeks ago is, do you actually need to be connected to the internet? That's a very good question, and the answer is no. There's not really good cellular service in many parts of the province where we want to use this. The reason we went with an internet network here is because of its reliability and robustness. We run our network cables through walls and buildings and leave them and don't touch them for years. When we run those cables, we know they're going to last a long time. And as an added bonus, they're really cheap. When you buy that stuff on a big spool, it's about 25 cents a foot. So populating your sprayer with this cabling is inexpensive and it's reliable. So we run everything into a network, and then we talk to this ECU that my colleague helped us develop, and then that will be what actuates the nozzles. So that is the overall layout of how our sprayers work. So when I spoke here last fall, this is the ATV that we were using for testing. That went really well. Everything worked. So through the spring, to get ready for our early spring application, we scaled this up to a commercial sized applicator. Instead of 12 nozzles, we now have 27. These are spaced at 20 inches apart, and we're using standard high pro, ultra low drip nozzle tips to make sure we have a good application rate. We traveled at about 3 miles an hour, and we had a tractor from Tidal just to help us, well, drive it. So we had an early season this year, as some of our other speakers have mentioned today. I actually tested kind of late in that for that early season on May 7th. We set up 4 test tracks to drive the tractor through that were each 120 meters long out in West River Station. And we put some water sensitive papers down in locations that had hair fescue and locations that didn't, because we wanted to see what we're hitting and what we're missing. So in 2 of the test tracks, those negative targets that were not hair fescue, we just used wild blueberry plants. In the other 2 test tracks, we picked out other weeds, sheep sorrel, moss. I think there might have been some hawkweed out there too that we used. And then as well, we wanted to test different confidence thresholds for this neural network. By default, if the neural network is 25% certain, it will draw a box on the screen. Now that seems low, but it is sort of the industry standard for a yes, this is here. But we wanted to test some different intervals because we wanted to make sure, 1, that we were hitting all the weeds, but 2, minimizing the areas that we didn't need to hit. So then we scanned those water sensitive papers and kept track of how much application was on each to actually see what we were getting. So our convolutional neural network, this video that I showed you earlier on is based on the YOLO V3 algorithm. And we put these fairly high resolution images through it to get an accuracy of around 75%. But the 2 metrics I really want to focus on here are precision and recall. They're based on true positives, and false negatives, so missed weeds. Precision, basically, that means if the sprayer is on, how often is it actually on for a weed? So with that old algorithm, 94% of the time, if that nozzle was turned on, there would be a weed underneath it. But recall is how many of the weeds we're hitting. Only 46%. That's not very good. Now, one thing to consider, though, is that we are getting multiple pictures of each weed. We're running these cameras at about 25 frames per second. So if you don't hit it on the first try, there are multiple chances to get that nozzle open. So that is something to consider. So this is just for a single image. What we did is, with these updates in technology that these programmers have done really good jobs at redeveloping these neural networks, we retrained with the new YOLO V5 model. We decreased our precision a bit, but really increased our recall to make sure that we were hitting every weed that we could. And one thing to note here too is the image resolution. We had to use really high resolution images a few years ago to get these really accurate results, but now we can shrink those images down. The number of pixels is 320 by 320 pixels with our new algorithm. So these images are a lot smaller, which means we can process them a lot faster and actually get these results in real time so we can open the nozzles quickly. Just as a visual comparison, this is the size of the image that we had to use a few years ago to get accurate results. And, as of last year, we can use images this size and get more accurate spraying results, which means that on those cameras that I showed you that we're using, we can run this algorithm at about 50 frames per second. It can process 52 pictures every second per camera, which is really helpful. We can really get those nozzles open quickly and hit as many of these weeds as we possibly can. So, as I mentioned, we wanted to test different confidence thresholds for where we open. At 20% more or certain, when we sprayed, we were hitting every bit of hair fescue that we wanted to hit. That's awesome. As we increased that, we started missing just one of those hair fescue plants that was very small. So to really help, so all of these are really great results, but ideally we keep that confidence threshold low to keep our recall high and at 100%, so we can actually make sure that we hit all the hair fescue. So we're not doing a worse job than we would with a broadcast sprayer. Now, in areas where we had weeds as negative targets, our precision dropped off quite a bit. We were sort of opening up the nozzles kind of when we shouldn't have been. So here's an example on our, some moss. We were really only supposed to be spraying for hair fescue, but as you can see, that water sensitive paper did get sprayed. In general, it depended on the weed. Something like sheep sorrel, it was really good at not hitting that and knowing that wasn't hair fescue. I think part of the problem here is that in our training data set, we had some pictures of hair fescue that were sort of mixed in or like right next to the moss. So that might have picked up the moss as a positive example. I'm still looking through the data to see how we can minimize those sort of errors. But similar to the other two test tracks, we did hit basically all of the hair fescue, which is what we want to see. Now, we didn't stop at hair fescue. The month after, we actually went out to a field in North River and decided to see if we could spray goldenrod. Now, the issue is my image data set for goldenrod wasn't taken in June, so the plants I had looked really different. So we collected a whole new data set of pictures, and then we labeled them. Now, when I developed the hair fescue data set a few years ago, I spent weeks and weeks and weeks just drawing boxes around plants. But now we can do this semi-automatically. If we label, let's say, 10% of our images, then train a neural network, we can have that neural network apply labels to a bunch more images. And even if it only gets 50% of those weeds, then I only have to draw 50% more boxes. So using the semi-automatic method, we're able to speed this up and actually get this working on more species of plants in a really quick fashion. So less than a week later, we were back out in the field actually using this spraying. So we sort of scaled this test back just through the size of the field. We have 2 test tracks instead of 4, and they're only half as long. But we did the same basic concept, put down the water sensitive papers in target and non-target areas to see what we get. With our training, so I've copied this table from the previous slide, but I added another column as well, which is our image count. So for hair fescue in our training data set, we had to use 3,700 images for training. We gathered a little over 4,000, and you have to save 10 or 20% for validating it to get these accuracy metrics. But we used 3,700 images for hair fescue. With goldenrod, we used 206 and got basically the same amount of accuracy. These newer neural networks are really efficient at finding those patterns with not a whole lot of data. Doing this, 3-4 years ago with Yola V3 wouldn't have been possible. But with only 200 labeled images, we are getting accuracies that meet or exceed what we were seeing a couple of years ago with much larger data sets, which is awesome. And as far as the spraying results went, it was largely the same as what we saw with hair fescue. We were hitting every bit of goldenrod that we drove over with the cameras. We were spraying those, and it was similar looking weeds as when it turned on what it was supposed to. If it was just blueberry crop, those nozzles stayed closed. There were some other leafy type plants that our algorithm confused and thought it might have been goldenrod. So overall, with this technology, we're going to see a reduction in herbicide use. We're still hitting all of the plants that we want to hit, but we aren't quite 100% efficient yet. So in Hugh's weed survey from a couple of years ago, for instance, hair fescue was in roughly a third of the fields that it was in. So it had about a 1/3 coverage. I could see realistically saving 50% of your herbicide in a hair fescue field if you're applying for hair fescue. You won't save 2/3. You are going to have some overspray because this is not perfect technology, but 50% would be ballpark what you could get for a reduction with this technology if you were to retrofit your sprayer. The future opportunities with this are that we have a master's student in our lab now who's looking at using drones for spraying fields. We're looking at drift patterns, what heights work. She's doing a lot of work on, seeing, how applicable this could be. And this is something that's already happening in the United States. They're using drones to spray a lot of their fields and a lot of crops. So we want to make sure it's safe and effective, so we can legalize it here in Canada too. Now, this 3D camera I showed you also comes in a 2D option. The real reason for the 3D on mine was just at the time, the supply chain. It was still during that COVID era. You couldn't buy any technology because it was all sold out. But now these are widely available. They have the same processor on board, the same color camera for taking the pictures, and they're about the size of a golf ball. Those would fit on a drone. You could do this automatic spraying with a drone theoretically. Now we're talking, 5-10 years down the line before you could see anything like this, but that's where this technology could be going in the not so distant future. So that's the sprayer update. I have some updates on the field scouting application as well. The first is this F2 detection. So Hugh and his team do a lot of work going out and collecting these stems and counting these buds manually. So we're trying to help make this semi-automated, in part to take some of the work off him, but in part so you can go to your fields and do it yourselves and have this nice fast algorithm that can do it for you. So we use a similar algorithm, but we're using one that's a little bit slower and more accurate. And there's a couple of reasons for that. When we pass our images in, they're basically from this perspective. We're kind of far away. We can't see the buds very well. So we do have to increase our image resolution, which slows down our processing, but that's okay in this instance. On the sprayer, we wanted to take 25 pictures every second because we need that to be lightning fast. But for this application, if your phone takes half a second to process that image, you don't really have to worry about missing anything. You don't have targets that are moving and need to be hit in real time. So I tested scaling up these images. Instead of just 320 by 320 pixels, I tried 640 and 960. As well, changing the size of that neural network. On the sprayer, I was using the nano version of this, which is very small. But where we, again, have the advantage of not needing real-time processing, we can use larger neural networks, which in theory will be more accurate. If you have more neurons that are being trained, they should be able to look at more features, find more features, and then get more accurate results. So with this, we used about just shy of 500 images for training. These pictures were collected in 2021, 2022, and this past spring. And then we labeled the buds on these as F1, F2, F3, or F4. Now, the summer student I had helping me with labeling, I should have supervised him maybe a little bit better because he grabbed them sequentially, which means that we have a lot more F1 buds than F2, than F3, than F4. And that can cause a problem because our data set's now unweighted for training. We do have more images that can be labeled to correct for this, which I'll talk about why we might need to do that in a minute when I talk about here, the results. So what we see here is each line corresponds to one size of a neural network, the nano, small, medium. And as you can see here, there isn't a whole lot of difference between 640 pixels squared versus 960, maybe a little bit better as we increase that resolution. But if you drop off and go to 320 by 320 pixels, like we have on the sprayer, those small features that you see on those buds really cannot be properly displayed in an image that small. So you do need, a slightly larger image to get those features to show so we can train our neural network. Overall, the medium-sized one did perform better here than our small and our nano, but not by a huge amount. So if need be, it wouldn't be the worst thing in the world to use that smaller neural network as long as that image resolution is high. You'll notice we're capping out at about 70% accuracy though, where we were seeing low 80s for our weed detection. And that is because of that unbalanced data set. If I go in and look at these stats per class, the F1 and the F2 that had the most training examples are in those low 80s right now. But F3 and F4 that didn't have enough training examples, that drops off. And that's what gets our average accuracy down to about 70%. So what I'm going to be doing in January and February is labeling some more of those images to get that data set more balanced. And then we should see those numbers come up and be similar to what we have for weed detection. And then the next stage of this is actually validating this. We did a study where we were using almost the same idea on ripe and unripe berries. So blueberries and then green and red. And then what we did is we actually cross-reference that with the weights after the fact, after we counted the berries. So we will want to cross-reference this to see how accurate this is compared to a human counter, compare with some of what Hugh and his team are doing, and then we can get a model out there that you can do this on your phone with. So the weed detection isn't just for the sprayer. We'd like to have that in the app as well. One thing that we have tried is the idea of Siamese neural network. So in the most recent weed survey, there were more than 200 species of weeds. And originally we needed about 4,000 pictures of each species, and which is a lot of data to collect. And I would like to graduate at some point. So I started looking at the ways I could cut down the time. These Siamese networks are used for handwriting verification and facial recognition on your phone. I mentioned that the last layer of neurons in the neural network is usually one neuron per class of thing that you're trying to detect, so one neuron per species. But instead, with these Siamese neural networks, you have two identical ones, and then you just have a list of numbers that represents that class. And then what you can do is just compare the two. And what this allows is that you could basically sign your signature 5 times, store it in one of these, and then it could compare that stored number to any signature that gets put in. And that's how you can verify your signature. So if someone else's signature is put into this, the numbers at the end will be different. And that works with your face too. So if you have Face ID on your phone, it's using this technology. You can take a few pictures of your face and then they can unlock your phone using this. So I thought it might be cool to try and harness this for these weeds. Only collecting 5 pictures of every species seems a lot more attractive than collecting 4,000. The real issue is that there's so much variability in how these things grow and what they look like at different growth stages that it became very difficult and complicated. That coupled with the fact that we only need a few hundreds pictures of every weed now as opposed to a few thousand, and the fact that labeling's quicker, I wouldn't say that this wouldn't, couldn't get this working, but it doesn't seem like it's the best path forward anymore. So if someone else ever wanted to pick it up, there's the information for you, but we're probably going to go with a more traditional style neural network, like what we did with the sprayer, for how we're going to do our weed classification. Conveniently, iNaturalist already has something like this working, and they put their data set online for free. So it's going to be hopefully easy for me just to pick out the species that are in blueberry fields from their data set, and that'll give me a lot of data already to cut down on this processing time. Finally, I want to touch on some disease detection. So one of my data sets is on of red leaf, and one of my lab mates, Connor, wanted to figure out if he could label images without labeling them at all. So I showed you that automatically generated definition of AI at the beginning of this presentation. Connor used that same technology. He passed in a picture and said, give me something that describes these features that I want to label. So he printed off basically a long list of examples of what might get a detector to label that automatically. Things like a red leaf plant, a cluster of red leaves or bright red leaves. And then he tested that with labeling software where he said, draw a box around the bright red leaves or draw a box around the red hued plant. He also did that with a segmentation mask as well, where instead of drawing a box, it would just draw around the pixels of those leaves, which for a human to label is really tedious and time consuming, especially if you're doing a few hundred. But he didn't draw those boxes. He just told the computer to draw a box around this, which sort of begs the question, what else can we do with this? Do I really need to be labeling all these weeds by hand? When we expand this out to more diseases, do we need to label these diseases by hand? As far as deploying this out to industry, it takes a lot of processing power to do this. So deployment's limited as far as what we can give out to you for developing your data set. But for us, we can create our data sets a whole lot faster using this technology and get this working on more weeds, more plant features, more diseases a lot more quickly because of this development. So that's Connor, who you might have had a chance to talk to this morning. That's really it for my presentation. I'd like to thank all of you for sticking around and for being members of the association, because